this is Captain Chaudhari. Today I'm going to speak about shear force and bending moment. What is stress? We will try to understand what is tensile stress. We'll try to understand what is compressive stress. Let us try and understand about the force. What is force? Force is rate of change of momentum. That is, force is equal to mass into change in velocity divided by time. So we can say force is mass into acceleration. And what is stress then? Stress is what is the force per unit area. Well, if we talk about a piano wire, there is this weight which is acting downwards and there is this tension which is acting upward. Both these forces are acting in one line. Both these forces are equal and opposite. The tension there and the weight downwards, these are the two forces, they are acting in one line. They create tensile stress. So what is tensile stress? So tensile stress can be considered as a force that is pulling that wire divided by the cross area. So what is the unit of stress then? Unit of stress therefore is Newton per meter square. In the maritime calculation, sometimes we may say that the pressure or the stress is tons per meter square, but actually tons or a kilogram is not a force, it is mass. And we are talking about a pressure being force per unit area. So actually instead of writing tons per meter square, it is more correct to write newtons per meter square or kilonewtons per meter square. Right? But we are doing the calculation and it is accepted fact that if we do the calculation and if the criteria is also described in the same unit, then it does not make a difference to the user. So it becomes user friendly that way. Pressure as well as stress both have the same unit, that is Newton per meter square, or Newton per meter square is also Pascal. 10 raised to 3 Newton per meter square will be equal to 1 kilopascal. 10 raised to 6 Newton per meter square will be 1 megapascal. And 10 raised to 9 Newton per meter square will be 1 gigapascal. These are the units of stress or the pressure. Now, I gave you an example where we can experience what is tensile stress. Let us say on ships you have these kind of tables where you have pillar in the center under the table which is bolted down to the deck. If you put some weights on top of the table in the center part, weights are acting downwards and reaction is upward. Both these forces are equal and opposite. They are acting in the same line. So this gives rise to compressive stress. The common thing in both is we have forces acting in opposite direction. Right? Forces are equal, acting in opposite direction, and they are acting at the same point. So here with a piano wire we can understand tensile stress, and with this pillar under the table we can understand compressive stress. Now we will try to understand what is shear force. But to understand shear force, let us say that there is a beam which is supported at the ends. Right? Throughout the beam there is a tendency to go down. Tendency to go down because of the weight of the beam. The weight is acting downwards, right? And to support the weight, there is reaction which is acting over here, reaction which is acting over here. These reactional forces and the weight forces, they are perfectly not balanced, in the sense they are not perfectly acting in the same line. Can I say that this part of the beam is trying to go up and this part of the beam is trying to go down? If there is a tendency that on one side the forces are taking the beam upwards and on the other side the forces are trying to take the beam downwards, then there will be a tendency to tear or shear, and this shear or tear tendency is perpendicular to the axis of beam. This kind of force, which is because of unequal forces on either side, or the forces which are opposite but not acting in the same line, will give rise to this tendency, and this particular force is shear force. Shear force in respect of the ship can be very easily understood typically by the concept of, there used to be a concept of alternate hold loading. Now, in alternate hold loadings, you were loading iron ore in 1, 3, 5, 7, etc. and the alternate holds were empty. Now, if an artist looks at this diagram or this way of loading, he would probably draw the ship this way, that this part of the ship or this hold wants to come down, this hold wants to go up, come down, go up, come down. This typically shows the tendency of the ship or the tendency of ship side or the hull to tear off or to shear because of unequal forces on either side. So we'll try to understand what is the effect of the shear force which acts on the ship. How the forces, when they act opposite to each other, right, they give rise to shear force. And how the moments which act in a different direction, that is clockwise and anti-clockwise about a point, give rise to bending moment. The shear force can also be visualized looking at the old type construction of the ship side, where we had the ship side plates. They were held together by the rivets. Now this plate wants to go up and this plate say wants to go down, but the rivet is the one which is trying to keep the plates together. Once again we have an example whereby on one side of the rivet there is upward force and the other side is experiencing downward force. And if we try to look at the rivet in a magnification, you will find that the rivet wants to shear off. So if the rivet is not strong enough, the rivet will shear off over here. We will try to understand the shear force with the help of an example of light beam or a weightless beam. We'll try to put the weightless beam on end support, say for example knife edge. Let's assume that there is a light beam which is 6 meters long, supported at the ends. There is no weight, and maybe we can place a weight over here of say 60 kg. Although we are dealing with kg, but in the end we will convert kg into newtons. The beam is in equilibrium. I tell my students, what is equilibrium? Equilibrium means state of rest. You can look at anything that is living or not living, as long as it is not making any motion, movement, it is in equilibrium. Now this beam is not doing a linear motion, so net forces must be zero. When the beam is resting like this, let us say this beam is A, B, C, D, E, F, G, and there is this reaction RA acting over here and reaction RG that is acting over here. And because the beam is not making any linear motion, the opposite forces are equal. So RA plus RG, which are acting in upward direction, should be equal to 60. This is equation 1. RA plus RG equal to 60. Also, the beam is not turning. The beam could turn if there was a pivot here, and the beam could turn clockwise, anti-clockwise, or the pivot was over here, a pivot anywhere else, but beam is not turning. So if the beam is not turning, then can we say that the net moments which are acting on the beam about any point, not only one point, about any point, the moment, that is the turning capability, is zero. That means if I consider that there is a pivot over here, that means the beam could turn about this point. The forces which are causing the moment, for example this force is vertical, but the moment is anti-clockwise. Now this 60 kg force is trying to turn the beam at a distance of 4 meters. So 60 multiplied by 4, that is 240 kg meter, is the moment. That clockwise moment is not able to turn the beam. That is because here is another force, that is RG, the reaction that is acting at G at a distance of 6 meter. It is trying to create, it is creating an anti-clockwise moment, that is RG multiplied by 6. But the beam is neither turning clockwise nor anti-clockwise because the beam is in equilibrium. Can we say that if we take the moment, that means if we assume that the pivot point is at A, if we take the moment about the left support, we will take the moment about the left support. when we take the moment about the left support, the clockwise moment equal to anti-clockwise moment, and therefore 60 into 4 is equal to Rg into 6. So 240 divided by 6, that is 40. So Rg equal to 40. So if Rg equal to 40, Ra should be equal to 20. So this is how invariably in all the cases what I tell the students, you take the moment about the left support and that will give you the value of the reaction on the other side. So wherever you have the supports for the beam, you should assume that a reactional force is acting at those points, and invariably about the left support, that is where the left side reaction is acting, you take the moment about that point. That means what we are trying to understand is, if the beam could turn about this point, this force trying to turn it clockwise and this reaction trying to turn it anti-clockwise, they give equal moments. That means clockwise moment is equal to anti-clockwise moment, and that equation gives me the value of Rg as 40 kilogram. Now what we try to do is try to find out what is the shear force and what is the bending moment curve for this beam, or what we are trying to find out is what is the value of shear force at all these points. If I consider any point, say for example C, then to the left of it, what are the forces which are trying to push the beam upwards, and what are the forces which are trying to push the beam downwards, right? That will give an idea of shear force at C. That means if I consider the point F, what are the vertical forces upwards to the left of that point is 20. What are the vertical forces acting downwards to the left of this point is 60. The difference of 60 and 20 is 40. That means shear force which is acting at F is 40. I don't have to worry about the other side, because if I do the calculations on the other side, I will get the same result. So that is the beauty in doing the SF and BM calculation. We need to consider only the left side or the right side. In effect, when I want to find out the shear force at C, then I just look at the left of point under consideration C, and I try to find out what is the net vertical force acting to the left, and that is the shear force at C. Whereas if I want to find out the bending moment at C, I once again look at the forces only on the left of C. I don't have to worry about so many forces, hundreds of forces to the right of C. Just the force which is acting to the left of C. And the only force which is acting to the left of point under consideration is 20 kg at a distance of 2 meters. And this force is trying to turn the beam which way? Which way? It is clockwise. It is clockwise. So 20 multiplied by 2 is 40. According to our sign convention, clockwise to the left of point under consideration will give me positive moment, and anti-clockwise moment to the left of point under consideration will give me a negative moment. Positive moment means sagging and negative moment means hogging. That means this force is trying to sag the point C. So that was in effect the meaning of shear force and bending moment. Let us do the calculation now. Let's make the table A, B, C, D, E, F, G. These are the stations. Okay. Now, shear force for the time being, the unit I would say is kg. Actually, the unit is Newton. We will convert it afterwards. At A, you can coolly say that the shear force is 0, because actually there is nothing to the left of the point under consideration, which is A. If I blank off the beam, if I blank off the point A, I don't see any force to the left of A. But if I come 1 micromillimeter to the right of A, that means this is a knife edge and it's slightly to the right of A. If I come, I find a 20 kg force upwards. According to our sign convention, the upward force to the left will give me the positive force and downward force will be considered as negative. So can I say at A suddenly the shear force is changing from 0 to plus 20? 0 to plus 20. If I place my screen at B or I put my hand at B, what do I see to the left of B? The only thing which I see, the only force which I see to the left of B is the upward force B. So can I say at B also the shear force is 20, at C also the shear force is 20, D also the shear force is 20, and E, once again there is a point force acting. Point force acting means the force is acting at a point. Now wherever you have point forces, you have to do two observations. You have to put the screen once slightly to the left of E and then slightly to the right of E. If I put the screen slightly to the left of E, I still find 20. And if I put the screen slightly to the right of E, I find 20, which is plus minus 60. That means plus 20 to minus 40. So what is happening at E? Once again, there is a point force acting at E, and wherever you have point force acting, the shear force will run from one value to other value. You had a point force here, it ran from 0 to plus 20. You have point force here, it's running from plus 20 to minus 40. And once again, you have done the counting to the left side up to here. So it's like a cricket board. Your score keeps changing. Now you have already counted up to here being minus 40, and if I place my screen at F, I still find minus 40. And over here at G, if I put my hand slightly to the left of the support, I will find the value minus 40, and then if I put the screen to the right of G, I will find minus 40 plus 40 becoming 0. So can I say at G the SF value is changing from minus 40 to 0. Now you can see the SF values are changing from the ranges from plus 20 to minus 40. So what we'll do is we'll take a scale 10 kg equal to 1 centimeter. So you write the scale here, 1 meter is equal to 1 centimeter for the beam, and then because the SF values are changing from plus 20 to minus 40, I've taken a scale 10 kg is equal to 1 centimeter. That is y-axis. Horizontal straight line represents a light beam or weightless beam, and you will also find that the SF runs vertically at all those points where you have point forces. One more observation, that is SF is 0 in the beginning and also at the end. The positive area under the SF curve is equal to negative area under the SF curve. So generally when you have drawn the SF curve, you should find that the positive area approximately is equal to negative area as it appears. Actually it will be perfectly equal. The shear force that is acting between A and F is 20 kg, and 20 kg means 20 into 9.81 is equal to 196.2 Newton. 196.2 Newton. That is 20 kg, and 40 would be 392.4. 392.4 Newton. To find out whether this bending process, whether this bending moment is sagging or hogging, I don't have to test on both the sides of point under consideration. I just need to look at one side of the point under consideration. In all my calculations, I'll be just trying to see the left side, left of the point under consideration. I don't want to duplicate the work. So just one side is good enough. So if I want to say, for example, find out what is the bending moment at this point. So what I do is I tell the students that you kind of put a vise here. You have seen the carpenter's vise, the rigid vise. So you try to make this point rigid. And then you see what are the forces to the left of the point under consideration. We find that this 20 kg force is trying to turn the beam about this point. The beam would bend like this. Okay? This force is trying to bend the beam this way, or this force is causing a moment that is clockwise moment, and the clockwise moment will be positive because it is to the left of point under consideration. So I would say that at C the bending moment is 20 multiplied by 2 and it is positive, that is plus 40. As I said, at A you can coolly say that the bending moment is 0. At B, if you had made the point B rigid, B is point under consideration, this force is trying to turn the beam or bend the beam at B with a moment that is 20 into 1. 20 into 1, that is plus 20. Similarly, at D, the moment would be 20 into 3, that is plus 60. And at E, it would be 20 into 4, that is plus 80. At F, what happens is, you have clockwise moment of this force. If this is a point under consideration, this clockwise force at a distance of 5 meters is causing a positive bending moment, that is 20 into 5. But this 60 kg is trying to cause a negative bending moment, that is anti-clockwise bending moment. Anti-clockwise bending moment to the left of point under consideration is negative, so it is minus 60. So 100 minus 60 is equal to 40. And let us look at the end point G. Whatever you do, I told you at end the bending moment has to come 0, right? This means your calculation is correct. Now at G, let us see, it is 20 into a 6, that is plus 120, that is positive 120, and minus 60 into 2, because this force is at a distance of 2 meters, so minus 120, totaling to 0. So we have seen that we started with A, assuming that the bending moment at A would be 0. At G, from the calculation, I got the total bending moment to be 0. If I plot, I need to take a suitable scale. You will find that the entire bending moment values are positive. So it is possible that the entire bending moment values will be positive or they will be negative. But when you talk about shear force, you must have equal area on the positive side and negative side. So you should overlay the bending moment on the SF curve itself, because you need to compare, right? One of the points which you must observe when we plot the bending moment curve is where the SF curve is changing direction, that means from positive to negative or negative to positive. That is the point where bending moment value will be maximum. We'll look at it. So we're talking about point E where the SF values are going from positive to negative. At E the bending moment value is 80 and that is the maximum value. Let's take a suitable scale, right? And that suitable scale I suppose should be 20 kg meter is equal to 1 centimeter. So it is 20, 40, then 60 and then 80. You get a straight line. If somebody draws the bending moment curve as a curved line, he will get 0 marks, because one of the most important things about the SFBM calculations is your curve should look principally correct. So to see the curve principally correct, a few things I'll tell you. SF and BM, both the curves, they start from 0. SF curve is horizontal straight line because it is a light beam. Where the SF curve is changing direction, you will have, at the same point, you will have the bending moment maximum. And the vertical run of the SF curve would indicate that there are point forces acting on the beam at those points. And one more thing, if the SF curve is horizontal straight line, the bending moment curve is slant straight line. But if the SF curve is of any other shape, that means if the SF curve is slant straight line or curvilinear, the bending moment curve will be curvilinear. We can see that the entire bending moment curve is positive, and positive according to our convention is sagging. So entire beam is sagging, and the maximum that the beam is sagging will be at point E. So this is your bending moment diagram. Now the maximum bending moment that is occurring is 80 kg meters. 80 into 9.81, that is 784.8. The value is 784.8 Newton meter is the maximum bending moment value sagging. So if the question says what is the maximum bending moment value and at what point is it occurring, so you should say that from the left support, 4 meters from the left support, the maximum bending moment value 784.8 Newton meter sagging is occurring. So that was the SF and BM of a light beam.